So we're recording now. So we're going to start out today with nickel 2 chloride aqueous reacting with sodium hydroxide. Somebody tell me out loud the name of one of the products.
NiOH.
Close. NiOH 2 because it's nickel 2. So if it's 2 plus on this side, it's 2 plus on that side. So that's one of our products. What's the other product?
Sodium chloride?
Sure is. Sodium chloride. So now looking at your solubility chart, are both of those aqueous? One of them solid? What are the physical states for these two?
They're soluble?
One of them is. One of them's not.
Says OH is slightly soluble, so not soluble.
Right. So it's a solid. And what about sodium chloride?
It's soluble.
It's soluble. Good. Tell me what I need to do to balance this.
Need to put a,
Make Na a 2, add another sodium.
On which side, a reactant or a product? Sodium hydroxide or sodium chloride?
Chloride?
Put a 2 here.
Yes. I don't know, honestly.
Okay.
You need it in front of the other one too, right?
Well, I've got one nickel on this side,
right,
one nickel on this side.
you need two sodium hydroxides on the
Okay.
product
Two
side.
sodium hydroxides.
2 sodium hydroxides, because that will give me 2 hydroxides. Remember to treat your polyatomic ions as a single unit. Makes it easier to balance. So now I have 2 hydroxides. I'm going to need 2 sodiums over here.
Yeah, so you need 2 sodium chlorides on the product.
All right. I'm balanced. Good, good. So here is what we call our molecular equation. What we write right here, this is often referred to as the molecular equation. The regular old balanced chemical equation. The molecular equation includes everybody. From the molecular equation, I can write what's called the complete ionic equation. In other words, things that are aqueous do not exist as this chemical. They're actually existing as ions in solution. So in other words, nickel 2 chloride is actually existing. Oh my goodness. Nickel 2 chloride actually exists as 2 separate ions in solution. It exists as nickel 2 and exists as a chloride ion in solution. It doesn't actually exist as Ni2. So if I had a beaker and I poured, or if I put some nickel 2 chloride in there and there's water, because this is soluble, what would happen is it would break up into its respective ions. In other words, in water, nickel 2 chloride exists like this. It doesn't exist as a single crystal. It dissolves or it breaks up into its ions. Sodium hydroxide does the same thing. How do I know that? Because it's aqueous. So that means if I poured in here some sodium hydroxide crystals, they would not stay together. They would separate into their respective ions. So because there's water in the system, then I have Na plus and OH minus. Now, I'm going to leave these unbalanced for right now. But here's what's happening in the actual chemical reaction. Here's what's happening. The two NAs, or the Na and the Ni, they don't really bump into each other because they have a similar positive charge. The type of interaction that's between them is repulsive. In other words, these two guys don't really interact because they're, I messed that up. These two guys, there we go. These two guys don't really interact because their like charges causes them to repel. So even if they come close to each other, they're going to repel due to their like charges. The same thing is going to happen between the chloride and the OH. They're not really going to attract each other because of their like charges. They're going to repel one from another. Well, the sodium and the chlorine, they might bump into each other, but they're not going to stay together. Or the nickel and the chloride are not going to stay together because they're aqueous. But if the nickel and the hydroxide bump into each other, then they form something that is insoluble. They'll form something that is insoluble. They'll form their product. If the sodium and the chloride bump into each other, because they're aqueous, they'll be attracted to one another. But they're not going to stay together as a single unit. They're going to break up into their respective ions again. So what we end up showing is that these two are actually existing as a mixture of ions in solution. It's only when the nickel and the hydroxide bump into each other that they stay, in a sense, stuck together and they form that solid product. If the sodium and the chlorine bump into each other, which they're going to be attracted because of their opposite charges, they're not going to stay together because they are also forming an aqueous product. What we end up showing is what's called a complete ionic equation. Now, this is a messy diagram. We're going to clean it up, but I want to show you where we get the ions from. In a complete ionic equation, you write things that are aqueous as their respective ions. So notice everything here that is aqueous, I've written it as ions because that's what it actually would be in solution. It would not be a single unit or an ion pair. It would actually break up into its respective ions. The only thing that I leave as a unit is things that are solid, liquids, or gases. In this case, I don't have liquids or gases, but I do have a solid. So let's rewrite our molecular equation and rewrite our complete ionic equation, and we'll write them both balanced. So I'm gonna write them both out and we're gonna write them as balanced. So here's our molecular equation. What we started with. So our nickel 2 chloride, aqueous, plus 2 sodium hydroxides, aqueous, which would yield nickel 2 hydroxide, that's our solid, plus 2 sodium chlorides, which are aqueous. So now we're going to write neatly our complete ionic equation. Things that are aqueous, we're going to write it as its respective ions. But we need to write it balanced as well. So when this ionizes, you get nickel 2 plus 2 chlorine ions, because that's what's in your formula. They're both aqueous. Okay. My sodium hydroxide, it's aqueous, so I'm going to write it as its respective ions, but I've got a 2 as a coefficient here, so that gives me 2 sodium ions and 2 hydroxides. And they're both aqueous. Copy my arrow. This is a solid, so I leave it alone. I write it just as it's written. Then I go to the last species. I've got a coefficient of 2 and it's aqueous, so I write it as its ions. Oop, I'm going to run out of room. And that is my complete balanced ionic equation. That includes everybody as they're actually reacting. So again, if you need a picture, if I was to pour in here some sodium hydroxide, if I was to pour in here some nickel 2 chloride, I would have a combination of nickel ions, chloride ions, sodium ions, and hydroxide ions. Then at the bottom, I would have a little pile of a solid precipitate. And the identity of that solid precipitate would be nickel 2 hydroxide. Let me know, so type a number 1, let me know when you have written out the complete ionic equation, because I know there's a lot of detail in that. Good, good. Good, I'm getting some feedback, good. Okay, I think I've got most of you. All right, from the complete ionic equation, we can write what's called the net ionic equation. And the net ionic equation, sometimes we think of it as the real chemical reaction. Okay, the real chemical reaction. What we do in the net ionic equation is we eliminate what are called spectator ions. Spectator ions, they don't participate in the reaction. They're present, but they don't actually precipitate, or they don't actually participate. Okay? They don't actually participate in the reaction. They don't actually participate. So to eliminate the spectators, what you do is you examine the complete ionic equation. And you cross out things that are aqueous on both sides. Okay. So the way that you identify the spectators is you look at the complete ionic equation and you eliminate the ones that are aqueous on both sides of the arrow. So for example, if I look up here, check out chlorine and chlorine, check out sodium and sodium. See how that they're exactly the same on both sides of the equation? In fact, they're even balanced on both sides of the equation. They're both aqueous. But when I compare this to nickel, I have nickel over here, but nickel is within a compound over here. So it is not the same on both sides of the equation. The same thing with hydroxide. Even though it's balanced, hydroxide is aqueous on this side, but it's within a compound in the product side. So I leave it alone. The ones that I've circled are the spectator ions. So in this case, our spectator ions are chlorine and sodium. They're the spectator ions for this chemical reaction. In other words, they have not actually taken part of the reaction. Okay, so you only eliminate things that are aqueous on both sides of the reaction. If they're not aqueous, you leave them alone. So only eliminate things that are aqueous on both sides of the reaction. After you've identified the spectators, then rewrite what's left. You rewrite what's left, and this is your net ionic equation. I don't know what the attendance code is. Somebody's asking me for the attendance code. I don't remember. We're on chapter 4. Somebody's asking me what chapter we're on. I don't remember the attendance code. Let me look and see if I can find it. Oh, thank you. Those of you that are remember the attendance code, thank you. We are on chapter 4. Okay. So let me see if we have any questions. Do you have any questions for me? Ask out loud. I'm not keeping up with the chat very well today. Go
Ms.
ahead and
Weir,
ask out loud. Yes, Gage.
how do you know when they're spectators?
The spectators are the ones, right here, Gage. The spectators are the ones that are aqueous on both sides of the equation. So,
Okay, so they don't change after they're go through a reaction.
correct.
Okay, cool.
They're aqueous on both sides of the equation.
Thank you.
Spectators are aqueous on both sides of the equation. All right. Any other questions? Okay, so I'm going to write out another equation. And I'm going to go ahead and give you here we go. Okay. This is a single displacement reaction, so check your activity series. Here's what I want you to do is determine the molecular equation. Of course, it needs to be balanced. And then from there, determine the complete ionic equation. And then lastly, determine the net ionic equation. So this is a simple single replacement reaction. You'll have to check your activity series. All right, let's check your progress. Let's check your progress. So according to the activity series, potassium is more reactive than hydrogen. So we get KOH plus hydrogen gas for this one. If you were stuck, I'll help you on this part. So those are your products. Anytime you have a metal plus water, you always get a hydroxide and a hydrogen gas. I believe this was on your handout, types of reactions that I gave you. But if you were stuck on what the reaction is, here's the reaction. So now let's see if you can balance it and determine the complete ionic equation. Okay, again, checking your progress. Turns out that this equation is already balanced, or is it? Not quite. This one isn't quite balanced, so I'm going to rewrite it. So I've got 1 potassium on each side, 2 hydrogens and 3 hydrogens, 1 oxygen. So I'm going to put a 3 here. That'll give me 6 of those. Oh, this is going to be fun. Okay, let me show you a trick. Well, before I show you a trick, does anybody have this balanced? I'm curious.
I have K plus 2 H2O is equal to KOH 2 plus H2.
I think where I get confused is that H2 has a -1 charge, right? And then, does that matter?
No, let's see. Potassium has a +1 charge on both sides, and hydroxide has a -1 charge, so that's balanced. The subscripts are all correct. You cannot change the subscripts unless I misheard. Did you say a 2
Just
here?
wanted to double check that, well, because I was just confused about how you added the 3 because I had put a 2, but I'll just let you go ahead and
No, I wanted to know if you guys had it
on
balanced.
H2, I just know that, well, I just know that that's why H2 is H2O because that's the oxide is a -2 charge, so that's balanced no matter what. You can't change the subscript. That's why I'm just confused on what to put before that, but I'll just let you work it out.
Okay, well, you can balance it by inspection,
Okay.
like we were doing. You can balance it by inspection, but I'll show you a little trick. Whenever you have, sometimes this trick works with oxygen. Let me get a pencil. In case I mess up my
I
own.
got it.
You got it? What'd you get?
So it's 6 potassium, 6 H2O. And the outcome is 6 potassium
Hydroxides.
hydroxide and 3 H2.
Okay. So let me tell you a trick, Bobby. When you have coefficients that are all divisible by the same number,
Oh, yep, there you go.
you can reduce them. So
Yep,
this would be like they're all divisible by 3.
yep.
So I could make this a 2, a 2, a 2, and a 1. It's not that yours was incorrect, Bobby, because yours was correct. It was balanced.
Right, I was doing it, I was trying to race here.
Oh, no, it worked. It worked. So, oh, I forgot my subscript. Solid, liquid, aqueous, and gas. Okay, so this is our, let me rewrite it, 2K plus 2 waters plus 2 KOH plus H2. This is a solid, this is a liquid, this is aqueous, this is a gas. Okay, so now we have our, this is our balanced molecular equation. So that's the answer to number 1. Let's try number 2. Let's write out our complete ionic equation. And the rule is if it's aqueous, we write it as its respective ions. If it's anything else, we leave it alone. So I chose this one on purpose because it's got both solids, liquids, and gases in it. So is this one aqueous? Tell me out loud, yes or no. Is it aqueous?
No,
So we leave it alone. You write it just as it is. The 2 waters, is it aqueous? Yes or no? Tell me out loud.
yes,
No, it's not aqueous.
It's a liquid.
It's a liquid. So you leave it alone. Looking at potassium hydroxide, is it aqueous?
Yes.
So you write it as its ions. Don't forget to keep it balanced. Uh-oh. And now the last one, hydrogen. Is it aqueous?
No,
No, so we leave it alone. So there's our complete ionic equation. So again, I'm emphasizing on the complete ionic equation, only things that are aqueous do you write as ions. If it's solid, liquid, or gas, you leave it alone.
Mrs. Weir, what's
Yeah,
the difference? What's the difference between liquids and aqueous? Like, what's like the difference, like chemically? Like, I mean, I just
aqueous
kind
means
of
it's mixed with water.
okay.
So in other words, KOH is a solid and I put it in water. That's different from liquid water. I don't mix water with water.
Oh, okay.
But isn't water made up of hydrogen ions and oxygen ions floating around,
A small-
polarizing each other?
A small percentages, a
Oh.
small percentage. And that's also temperature dependent. So the hotter the temperature, the more ions you have, but it's a very small percentage. All right, last step, the net ionic equation. We have to get rid of the spectators. Do we even have any spectators on this one?
Nope.
No spectators. So this is kind of a unique example in that the complete ionic and the net ionic are the same because there are no spectators. Remember, spectators are aqueous on both sides of the equation. So no spectators in this reaction. So it's the same. Uh-oh. So why did I take time to show you about molecular, complete ionic, and net ionic equations? The reason is because sometimes you can write out an equation and a reaction doesn't actually occur. Sometimes you can write out an equation and a reaction doesn't actually occur. And I'll show you what I mean. I'll show you what I mean. Here's another example. Let's say we take potassium nitrate and sodium chloride. And we allow them to react in solution. If we look at the solubility chart, we'll find that the two products are aqueous. Now this equation is balanced. Okay, so that's our molecular equation. Let's go ahead and figure out the complete ionic equation. So you tell me what to write. Do I write this one as ions, yes or no?
Yes.
I sure do. So I've got K plus NO3 minus plus, do I write sodium chloride as ions, yes or no?
Yes,
How do you know?
because it's aqueous.
Very good. All right, now I come to the product side, sodium nitrate. Do I write that as ions, yes or no?
Yes,
How do you know, Gage?
because it's aqueous.
Good job. And the last one, potassium chloride. Do I write it as ions, yes or no?
Yes, because it's aqueous.
Good job. So I've written my complete ionic equation. I've written my complete ionic equation. Now I'm going to do my net ionic equation. Where I eliminate the spectators. And as a reminder, spectators, they are aqueous on both sides of the arrow. Okay. So when I look, I've got one potassium, one potassium. I've got one nitrate, one nitrate. One sodium, one sodium. One chlorine, one chlorine. Did I just cross out everybody?
Yes.
I sure did. In this example, all were spectators.
So there's no reaction.
Exactly. That can be frustrating to chemistry students. I did all this work, and what do you mean there's no reaction? There's no reaction. What you have is a collection of ions. Remember that the evidence that a chemical reaction has occurred is that there's a change of heat, there's a change of color, there's, an odor, or you form a solid precipitate, or you form a gas. None of those things are happening in this reaction. Therefore, no reaction. So one of the advantages of being able to write a complete ionic equation is you can tell if there's no reaction or not. Nothing happens. Nothing happens. So if everybody's aqueous on both sides of the arrow, you don't have a reaction. Everybody's a spectator. See, everybody's aqueous, everybody's a spectator. There's no reaction.
Ms. Weir,
Yes,
the nitrates do not break up?
no, they hang out together. All right, a lot of detail on this slide. Let me know when I can go on to the next handout or the next page. Type a number 1 for me when I can go on to the next page, unless I have any more questions. Okay, good. You're keeping up well. Okay, last type of chemical reaction. Last type is what's called an oxidation reduction reaction. An oxidation reduction reaction sometimes are called redox reactions. These types of reactions, they involve a transfer of electrons. Okay, they involve a transfer of electrons. And it's really kind of like two things happen at once, always, always. Somebody's going to be oxidized. The one that gives away electrons is going to be oxidized. And the reduction part is the one that accepts electrons. And I need to send a handout to you in the chat window. On how to determine oxidation numbers. That's not it. Let me look for this real quick. Oh, I thought I had a handout for you. One in the book. Um, I thought I had a handout for you, and now I don't know what I did with it. On oxidation numbers. Well, that's okay. We can do it without the handout. We'll do it without the handout. Okay.
Mrs. Weir, I have a question.
Yes.
The oxidation numbers would be the same as the oxidation states I have here in my periodic table, right?
Yes. Same
Okay.
thing. Same thing. Hmm. Okay, actually, I do have a handout for you, but it's like it's part of another handout. Here we go. I found it. The one I wanted to share with you. Okay, let me send this real quick. So check your chat window. I'm sending a handout to you right now. Check your chat window. I'm sending a handout to you right now, and it's got like 4 pages to it. This is the booklet that I usually let you use for your final exam. There's 4 reference things in there. The first page has your solubility chart and your activity series. You should see it on the screen now. Scroll down to the second page. And this is what I want you to look at. Rules for assigning oxidation states. Look for that. Yes, Carol, I'll post it on Blackboard. Carol, are you unable to download stuff through the chat window? Okay, let me send it in Blackboard right now.
I think
Does
the
it-
problem is that we have to have PDF in order to open it. And
Mm,
so, well, that's how, like, I tried to download it and open it, and it said that I needed a PDF to look at it.
a PDF reader? Are you using a Chromebook?
No, I have a laptop.
Okay, I'll send it. There are free Adobe Acrobat PDF readers. You can get those online. In fact, I think you can get it in your student account because you have I can't type and talk, sorry. All right. Okay, there you go, Carol. I only have it as a PDF, but I sent it in Blackboard in case you can't open it through the chat window. But all right, so let me show you how to use this chart. First of all, what is an oxidation state? Well, I'm getting ahead of myself. So if you can't download through chat, check your Blackboard email, your Blackboard course messages. I just sent the document through Blackboard course messages. Okay, so we'll use this as an example. Now this is a burning of an organic compound. I think we covered this before. This is a burning of an organic compound, but it's also an example of an oxidation reaction. One of the things that can tell you that something is an oxidation reaction is oxygen is a great oxidizer because it loves to give away electrons. So when you react with oxygen, it's going to be an oxidation reduction or redox reaction. But let me show you how you can use your chart to figure out that this is an oxidation reduction reaction. We're going to have to determine what are called the oxidation states, or sometimes it's called the oxidation number for the nonmetals. And what the oxidation state or oxidation number is, that is the charge as if it were a metal. The charge as if it were a metal. And you actually already know a lot of these already. A lot of these you know already, but there are a few rules. So we're going to go through and determine the oxidation states of our reactants first. So looking at your handout, and I'll put the handout on here. Looking at our handout, rule number 1 says the oxidation state of an atom in its elemental state is 0. So looking at our reaction, when I look at oxygen in our reaction, oxygen is in its elemental state. Oxygen is in its elemental state. Remember that it's diatomic. So this is its elemental state. So its oxidation number is 0. In other words, it has no charge. When I look over at hydrogen, according to the handout, in rule number, go back here, rule number 4, oxygen in its covalent compounds is +1. Oxygen in its covalent compounds is +1. So looking at my compound here, hydrogen is going to be +1. Now, I don't know what the oxidation state is of carbon. I'm going to have to determine what it is. And you've seen me do this before when we were trying to figure out the charges on metal ions. But I'm going to determine what it is. I'm just going to call it some number X. Then I'm going to add that to 4 hydrogens who have an oxidation state of +1 each. And the overall oxidation state of the whole molecule is 0. So 4 times +1 is 4. The oxidation state of hydrogen, or the oxidation state of carbon in this compound is -4. Now I'm going to figure out the oxidation states on this side of my equation. So starting with water, according to my handout, I'm not sure what rule it is, you'll have to tell me, but which rule says that oxygen is -2 in covalent compounds? What rule is that?
Rule 3.
Rule 3, okay. So this is -2. So hydrogen is going to be some number times X, or some number times 2, because there's 2 of them, added to -2 is going to be equal to 0, because that's the charge on oxygen. So 2x minus 2 equals 0. So the charge on each hydrogen is going to be +1. See if you can figure out what the charge on carbon is going to be over here. And I'll give you a hint. The charge on oxygen, by rule 3, the charge on oxygen in its covalent compounds is -2.
+4.
Very good, +4. So -2 times 2 equals 0, plus some number. And so if you solve this, so we say that the oxidation state of carbon is +4. Whenever you state oxidation states, you have to say plus or minus. You can't just say, well, it's 4. You have to say if it's +4 or whether it's -4. So now that we have figured out everybody's oxidation states, let's compare. So we're going to make a chart, reactants versus products. And now we'll do our atoms, carbon, hydrogen, and oxygen. If I look at carbon on the reactant side, it's got a charge of -4. If I look at carbon on the product side, it's got a oxidation state of +4. I said charge, I meant oxidation state. If I look at hydrogen, it's +1 over here, +1 over there. If I look at oxygen, it's 0 on this side and it's -2 on that side. Do you see how I made my chart, just comparing what they are on each side? By the way, we didn't bother to balance this, but that's okay. Because if we had to balance this, we'd find out that there was 2 of these. And so the overall charge will be -4. But here's what I want to point out to you. This guy is a spectator. In other words, he doesn't change his oxidation state, so he's not part of the reaction. Who are the only two atoms that are taking part in this reaction?
Carbon and oxygen.
Carbon and oxygen, because they're the ones who are basically changing or exchanging electrons. So you have to think for just a little bit. Is carbon gaining or losing electrons? Let me help you out. Let me draw a little number line.
Is it losing?
Here's +4, is -4. It goes from -4 to +4. So somebody said it's losing electrons. When you're becoming more positive, you lose electrons. If I look at oxygen, it's going from 0 to -2. It's becoming more negative, so it's gaining electrons. So that means in this reaction, carbon, you tell me, is it oxidized or is it reduced?
It's oxidized.
Yeah, it's oxidized.
So this is like the regular combustion equation.
Yep.
Okay.
Not only is it a combustion equation, it's also an oxidation reduction.
Okay. So this is what this would be showing is fire burning on wood, for example, or something like that, right?
This one would be like, that would be an example of an oxidation reduction reaction. This one is actually like if we were in the lab lighting our Bunsen burners.
Oh, because that's methane, right?
That's methane.
Okay, I got you.
But burning wood would be burning sugar. And so, yes, because you get the same products. In fact, if you are a biology major, burning wood and burning sugar are the same. We just call it the electron transport system.
That's cool. I didn't know that.
Yeah. So carbon is oxidized because it's losing electrons. Oxygen is reduced because it's gaining electrons or it's gaining negativity. You with me so far? Okay, last little bit. Because carbon makes it possible for oxygen to be reduced, we call carbon the reducing agent. And because oxygen allows carbon to be oxidized, we call it the oxidizing agent. So I know what you're thinking, or maybe I know what you're thinking. Mrs. Weir, are you telling me that the reducing agent gets oxidized? Yes. Are you telling me that the oxidizing agent gets reduced? Yes. That's what I'm telling you. Okay, I have run out of time for today. When I see you on Monday, I'm going to give you an updated calendar. I decided to slow down on writing chemical reactions, not try and cover them all in one day. I decided to slow down a little bit, so I'm going to have to readjust our calendar. So look for a new lecture calendar on Monday. I'll post that. I'll probably post it later today, but I'll introduce it on Monday. The other thing is no labs this week because we had the holiday on Monday. So if the Monday group doesn't have lab, then the Wednesday group does not have lab. Monday was a deadline and many of you met the deadline. Thank you. I spent most of yesterday grading. I'm not finished grading. I'll be updating probably the rest of the week, the lab grade book. So you'll see your grades changing up until probably Saturday. I want to go golfing on Saturday, so my goal is to get everything graded Friday afternoon. So look for the grade to be updating. So yeah, no lab meeting. If you notice on your schedule for lab, we have nothing due this week. There's nothing due and there's no lab activity. So if you turned everything in on Monday, you get the week off. Good job. Good job. Any questions for me before we sign off for today?
Miss Weir,